Today we'll talk about a problem on electromagnetism. The problem states that a superconductor wire shaped in a ring of radius r originally carries no current. A magnet is moved along the axis of the ring which changes the flux by an amount delta phi b. Show that the current in the ring is given by Ne square A square delta phi b divided by twice Rm, where A is the radius of the wire and A is very less than capital R. N is the density of the conducting electrons. E and M are the charge and mass of the electron respectively. So in this problem we have to deal with superconductor. So at first we have to understand what does it mean by a superconductor. What is the difference between a superconductor and a regular conductor or a resistor? A superconductor does not have any resistance. What does it mean to have resistance? So let's say this is a resistor. It has some resistance, let's say capital R, and we apply some potential difference across the resistor. Let's say this is V, and a current I flows through this resistor. What actually happens is, due to applying a potential difference across the resistor, an electric field is created through this circuit like this. This is the direction of electric field. I have shown them through these green arrows. Due to this electric field, a force will be applied on the electrons in this resistor. But when we apply some force on a particle, the particle should accelerate, and that means the velocity of the particle should increase. But if the velocity of the electron increase, the current through this resistor should increase. But what we see is a constant current flow I through this resistor. That means the velocity of the drift speed of the electrons or through this resistor is constant. What actually happens is a resistive force actually counterbalances the electric force. When an electron starts moving through this resistor, through this circuit, it collides with other particles, and that's why the velocity of the electrons actually cannot increase. It actually in average remains constant. But in the case of a superconductor, there is no resistive force. The electrons can move freely. So if I apply a potential difference across the superconductor, the velocity of the electrons will keep increasing. The electrons will keep accelerating. And whenever I stop applying the potential difference, the electrons will still keep moving with a constant velocity. It will not accelerate, but it will keep moving with a constant velocity. That means the current will keep flowing. But in the case of a resistor, if I stop applying the potential difference, the current will stop flowing. So is the energy is conserved in these two cases. As the potential difference V is applied across this resistor and the current I flows through this resistor, some work is done, and the per unit time the work is Vi. And this work done is converted into heat. A heat is radiated from this resistor. But in the case of a superconductor, the work done is not converted into heat. Instead, it converts into the kinetic energy of the electrons. As long as I apply a potential difference through a superconductor, the velocity of the electrons will keep increasing and the kinetic energy will increase, and that means the work done here is converted into the kinetic energy of the electrons. So that's the difference between a resistor and a superconductor. Let's talk about the problem we have here. In this problem, we have a superconductor which is shaped in a ring of radius r. Okay, and a magnetic flux is changed by an amount of delta phi b through this circular loop. And we know by applying Faraday's law that due to the change of magnetic flux through this loop, electromotive force will be induced across this loop. And if the electromotive force is epsilon, this will be equal to the rate of change of magnetic flux through this loop. And let's say the change of magnetic flux delta phi b occurs in a time interval delta t. So that means the rate of change of magnetic flux is delta phi b divided by delta t. So as we have discussed earlier, when we apply a electromotive force or a potential difference across a superconductor, the, the velocity of the electrons will keep increasing due to the work done by this electromotive force. And that means the current through this superconductor will also keep increasing. And in this problem, the current is initially 0. And due to this induced electromotive force, the current through this superconductor will keep increasing. And let's say after the time period delta t, the final current is I. And let's assume that in this case, the change of magnetic flux is uniform here, and that means the induced electromotive force is constant. So the rate of increase of this current will also be constant, and so the average current in this time interval delta t will just be the initial current plus the final current divided by 2. That means the average current in this case will be I by 2. So that means the average power consumption during this time interval delta t will just be the electromotive force, that is epsilon, into this average current, that is I by 2. So the total work done during this time interval delta t will just be the average power into the time interval delta t. So this is the work done during this time interval delta t. So this will be equal to the kinetic energy of the electrons after the time interval delta t, because the work that is performed here will be converted into the kinetic energy of the electrons, as we have discussed earlier for the case of a superconductor. So what is the kinetic energy of the electrons? This will be half the mass of the conducting electrons into v square, where v is the drift speed of the electrons. So what is the mass of total mass of the electrons? This will be just the mass of a single electron, which is given by m, small m, into the total number of electrons, total number of conducting electrons in this superconductor, into v square, where v is the drift speed of the electrons. So n is the total number of conducting electrons. Now from this equation we have epsilon delta t is equal to delta phi b. We will substitute epsilon delta t for delta phi b. So we have delta phi b into I by 2 is equal to half m. So what is the total number of conducting electrons? This will just be the number of conducting electrons per unit volume, which is given here by small n, into the total volume of this superconducting loop. And let's say the total volume of this superconducting loop is W. into V squared. Now we have to find out the total volume W. The loop we have here is shaped like a ring, and the radius of this ring is capital R. Now let's cut this ring here. Let's say this point is capital A, and straighten this ring like this. So this is the ring. I just cut it here and straighten it. So this point is A, and this point is also A. So these two are the same points. So now what is the length of this wire? This will just be the circumference of this ring, which is twice pi r. And we are given that the radius of this wire is A. So that means the cross-sectional area here is pi a squared. So we have now that the total volume W is equal to, so we can consider this as a cylinder that has height twice pi r and cross-sectional area pi a squared. So we just have the total volume is twice pi r into pi a squared, which is equal to twice pi squared a squared into r. Now we plug in the value of W here. So now we have delta phi b, and 2 is cancelled from both sides. So delta phi b into I is equal to mn, and W is equal to this thing. So twice pi squared a squared r into v squared, where v is the drift speed of the electrons. Now we know that the current I is equal to the number of conducting electrons per unit volume, which is n, into the cross-sectional area. So in this case we have the cross-sectional area is pi a squared into the drift speed, which is v, and the charge of a single electron, which is e. So we just plug in the value of I here. Now we have delta phi b into n pi a squared ve equal to mn twice pi squared a squared capital R into v squared. Now n is cancelled, a squared is cancelled. We can divide both sides by pi also, and also dividing both sides by v. So finally we have delta phi b into E is equal to twice pi m r into V. So we have V is equal to delta phi b E divided by twice pi m r. So we are almost done. We know that the current I is equal to the number of electrons per unit volume into the cross-sectional area, which is pi a squared here, into this velocity, the drift speed, which is, we have found out that delta phi b into E divided by twice pi m r into the charge of a single electron, which is E. Now pi is cancelled, and ultimately we get I is equal to n a squared e squared delta phi b divided by twice mr. So which is the final answer. Thank you for being here with us, and we hope you have enjoyed this tutorial.